Okay, so this is going to be, I broke these sub-elements up into smaller groups just for recording purposes, so you don't have to sit through and watch 2 hours of video if you want to watch them. And following along with Romanchuk's book, he starts off with kind of basic electronics before you get into the operations and rules and regulations, which is very boring stuff, and it's all memorization. And I kind of like the way he organizes it. Some of the units they're going to deal with is a charge, which we represent as Q. And it's usually measured in coulombs, named after a French scientist named Coulomb.
What?
Yes? Was that a question? You must be breaking up.
Must be off frequency.
Okay. If you manage to get through, we'll just ask it again. We deal with current, and we use the letter I to represent current, and it's a measurement of the movement of charge. And we measure that in amperes, another French scientist. Then we have force or potential, and we call it electromotive force, which is why we use E to represent voltage. And we measure that in volts. This time it's named after a guy named Volta, and I don't remember what he was. He wasn't French. And then resistance, and this is where Mr. Ohm comes in. And we measure resistance in ohms, and he's the one that developed Ohm's law, which is the opposition to current flow. So voltage is what causes current flow, which is the movement of charge, because that's the force that causes it to move. Resistance opposes that current flow. And that's kind of the basic of electricity, which Benjamin Franklin called electric fire. And that's how they dealt with it. We have what we call direct current and alternating current. If it's direct current, it only flows in one direction from what we designate as positive to negative, although that was arbitrary when it was decided. But we still follow that convention today. If it's called alternating current, it reverses direction. Not just goes to zero, it actually goes from positive to negative and back. And that's what we call a cycle, as it varies from zero to some positive value, through zero, through some peak negative, and back to zero, which would be a complete cycle. We have conductors, which are normally metals that have basically 1 or 2 valence electrons in their outer shell, which makes it very easy to displace that electron. In other words, provide enough energy where it's called a free electron and it can move and recombine with another atom that may be missing an electron, or possibly add and give it an excess electron. And that's where the charge comes from. Electrons have a negative charge. In the nucleus of the atom, the positrons have a positive charge, and they're equal, but opposite. So in a normal atom, there's no charge because you have an equal number of protons and an equal number of electrons, and they cancel each other out. If you displace an electron, then the atom becomes a positron because it has a positive charge, and then somewhere you have that electron with a negative charge. And we'll get into that a little bit more later. As the opposite of conductors, we have insulators. And these are materials, atoms, which have almost a full valence shell. So it's very, very hard to get a free electron out of those. So it will not conduct current or charge. And that's how charge moves, as electrons moving from atom to atom. Okay, a little bit about Benjamin. He actually named a lot of these things that we deal with, and we're still dealing with them, like potential and current and conductors, and which was positive and which was negative. Turns out he got that one backwards because it's really electron flow or charge flow. But they didn't understand all that at the time. So we still have what we call conventional current flow that goes from positive to negative, even though electrons are traveling from negative to positive. And you see that in a vacuum tube, where the electrons actually travel from the cathode to the plate. We won't talk about vacuum tubes until general, and they're still around. And they're on the test on the general.
They're not manufactured anymore.
Oh, yeah.
They are?
Oh, yeah.
Yeah.
Oh, yeah.
Really? Is it just to repair things, or do they make radios?
Oh, yeah.
Do radio
From scratch with vacuum tubes?
Yeah.
power.
They don't
Linear
make
amp-
TVs that way.
Power amplifiers are still manufactured with tubes, especially
Really?
high power radio stations or
Wow.
all tubes.
Huh. Does it
Hi-fi, the
benefit?
good hi-fi
Does that
stuff.
benefit?
Yes,
It must be, because they're still doing it.
it's easier to make high powered vacuum tube than it is a transistor.
Yeah.
Ah, okay.
And
And they're much more robust. You can't kill it vacuum tube as easily as you can.
all of your rock and roll musicians use tube amplifiers because they sound different.
They distort better.
Yeah, they're colored.
And you don't put a KW through a transistor.
Not most of them.
What's a KW?
Kilowatt.
Oh, okay, sorry. I thought it was something.
And we'll get to that shortly.
So in common practice, direct current is like batteries. You
Right.
have AA, AAA, any kind of batteries, typically direct current. You plug on your wall is, so it's AC, it's AC, that's all. So that's just the different types of these examples of DC, AC in the house.
So radio waves are alternating current. And actually, radio waves are anything above 0 hertz to infinity, which is another test question. Okay, so let's talk voltage. The electromotive force, or the potential that actually,
That's backwards.
what?
The diagram showing current flow. He's showing the conventional.
Conventional current.
Conventional? Okay.
Yes, yeah, we'll deal with conventional
All
current
right.
until we get to semiconductors.
Ernie and I will never, we'll never like the positive and negative.
It's because we can't see the electrons with our eyes.
That's right, only positive.
Yeah.
Yeah.
And actually,
we were-
that's a misnomer. The electrons don't actually move like you think. Electrons
Charge.
travel at 0.01 millimeters per second,
Super slow.
which is super slow. But charge moves at the speed of light. Or almost.
And don't confuse me with
All right. Okay. This is the force that can cause charge to move. In other words, have a free electron actually with its charge move to another atom and transfer that charge. And you get kind of well, can't think of the word right now. One example, and that was one of the few demos I had in my physics class. is they took a tube, filled it full of ping pong balls and to represent the atoms. And if you tap the ping pong ball on one end, one flies out the other end at not quite the speed of light, but basically instantaneously. Now, the ping pong ball didn't hardly move at all. But the force, when you tap the ping pong ball, went from ball to ball to ball to ball to ball, which is the way charge moves in conductors.
They have that little thing that has the strings come down, they have a metal ball on, you pick up one. They take two of them out, drop it, two of them go out there. The ones in the middle just stay where they are.
So it's really the charge that's just getting transferred around. And some of these electrons may go in the opposite direction after it's moved. You know, and normally they're just going around in random, even if they're free. And I think I've got a little chart with that. So that's basically the force, and we measure it in volts, represented as E. In this case of this diagram, we have a battery that's got some voltage through a resistor, and there's some current that flows depending on the ratio of that voltage and resistance. So the higher the voltage for a given resistance, the higher the current is going to be. And we'll talk about that when we do Ohm's law after we get through current. So your first question, what is the electrical term for the force that causes electron flow?
Voltage.
Amps.
Let's see. Electromotive force or voltage.
Smarter than the average bear.
Amp hours is just a unit of charge, which represents 3,600 coulombs. Because it's 1 ampere for an hour. And an ampere is 1 coulomb per hour. And just, you don't need to remember, a coulomb is 6.24 times 10 to the 18th charges, equivalent to electrons. Capacitance, which we'll talk about later, is the ability to store energy in an electric field, and inductance is the ability to store energy in a magnetic field.
Farads versus Henrys.
Say what?
Farad versus Henry.
Farads and Henrys, right? You've been through class.
Oh.
Direct current is, like we said, the flow of electrons or charge in a circuit. Whereas if we call it conventional current, we go positive to negative. If we look at charges, they're actually going in the opposite direction. In most of the questions, you're going to be referring to conventional current. So it will go from positive to negative. And we measure it in amperes, and we use A to stand for amperes, named after Charles, I forgot. The French guy named Ampere. So what's the name for the flow of electrons in an electric circuit? Current. Current. So voltage is the force that causes the flow. Resistance is the opposition to the flow. Capacitance, again, is the ability to store charge in an electric field, and we haven't got to capacitance yet. And current is the conventional current, or even the electron flow, the movement of charge. Okay, electrical current is measured in which of the following units?
Amps. Not supposed to just yell them out.
Sure, sure.
Absolutely.
I'll hear the one out of the house.
And if you're wrong, we won't say boo.
On your test, you'll have questions like that. If you look
These
at
are the
previous
questions.
Questions, you'll see the answer to that question.
Okay.
Yeah, these are the actual questions out of the pool. Now, on the answers, I've added this other stuff of what those things, the wrong answers are. So amperes is a measure of current flow. It's actually coulombs per second. Ohms is the measure of the opposition. Watts, which we haven't got to, is a measure of power or the rate of doing work. And volts is the electric potential or force. Did I hit the wrong one? We just had that slide.
Well, it's different. You just talked about direct current, explaining direct current on that slide,
Oh,
then you're coming to all of them.
all right. But we already talked about direct current. Alternating current. The polarity or the current reverses. It's called. It's volts alternating current. We normally talk at 120 volts AC. Technically, it's 120 volts AC RMS, which I don't know if we get to in the tech or not. It's the equivalent of the DC voltage. So 120 volts AC would light a light bulb the same as 120 volts DC. Whereas the AC voltage peaks are going to be much, much higher than 120 volts, like 2.8 times. But essentially the area under the curve is going to be the 120 or the equivalent to DC. Typically, an AC waveform is going to be sinusoidal, which means it follows a nice sine wave. I think I have one later showing how you generate a sine wave. A lot of times it will be, it might be a square wave, a triangular wave, some other distorted form. Any of those waveforms can be, or is essentially a combination of sine waves of different frequencies and amplitudes. So a square wave, for instance, is the sum of all of the odd harmonic sine waves. In other words, if you got a, say a 1 hertz square wave, it would be composed of that 1 hertz sine wave, a 3 hertz sine wave, a 5 hertz, a 7, on up to infinity, and actually generate a square waveform instead of a sine waveform. So the current alternates between positive and negative. It has to actually cross zero to be called alternating current. If it doesn't cross zero, it's what we call pulsing DC. Whether it's negative and going to zero and back, or if it's positive to zero and back. If it doesn't cross zero and change polarity, then it's direct current and not alternating current. Oh, this is typically how a sine wave is generated. If you think of this circle with 360 degrees, as you rotate that radius around the circle and look at the sine of that angle, which is a trigonometric function, if you remember that from high school, and look at the sine, which would be the height of this radius as you rotate around, and plot it versus time or degrees, it plots out this perfect sine wave. And that's where all of the math and stuff in electronics and physics is all based on this. And we tend to do things like make it simple, and we say that the single radius for a circle, we call it a radian. And because of the formula, 2 pi r, there's 2 pi radians around the circumference of the circle. So therefore, in a wave form, there's 2 pi radians. So you'll see when we talk about phase and things like that, we do it in a lot of the formulas. You'll see the pi and 2 pi showing up. That's where they all come from. Probably more than you need to know right now, but
The shape of the wave, that would be the sine wave, really was important on that diagram. If you took an oscilloscope, a measuring device, you know, if you see stuff and put it in your wall socket, 120 volt AC, you'd see something on the display that's what your voltage and current coming from your wall out looks like. If you put a measuring device called oscilloscope on there. With it. You
okay.
really see an alternating voltage. Alternating current.
So which of the following describes alternating current? This is one you should read carefully.
See,
Let's see. Current alternates between positive and negative. Okay, if it's positive to 0 or negative to 0, it's called varying DC. And we'll see that when we talk about rectifiers.
Going back to the diagram that you saw, started at 0, then it went up positive, came down across the 0 line, it went negative. So that's a sine wave, that's alternating current, that's what
Right.
one positive, negative, negative.
And it doesn't have to be symmetrical. I mean, normally that's a good thing, but it could have a DC offset. So the only thing that matters is that crosses 0 and changes polarity. Okay, the other thing when we talk about AC is frequency. And that's just a measure of how many times per second it changes polarity. And we call that a cycle. And also a period if we measure it in seconds, which is the the time it takes, where frequency is how many times it does it per second. So period is the number of seconds it takes for a cycle. Frequency is the number of cycles that happens in a second. And one is a reciprocal of the other. In other words, 1 over the period is the frequency, or the period is 1 over the frequency. And we use the term hertz now to represent frequency. That was named after this German physicist named Hertz. It wasn't all that long ago, we used to call it cycles per second. And somebody decided to honor Mr. Hertz, and now we use hertz instead of cycles per second. But it's still the same thing.
Shorter than saying, it's like,
And Hertz didn't live to be that old. Did he electrocute himself?
I don't know. So what describes the number of times per second an alternating current makes a complete cycle?
wave. Oh, frequency, sorry, frequency.
so in your house, your wall outlet again, 120 volt AC, right? How many, anybody know the cycles per second of your wall outlet, 120 volts?
60.
Or the hertz?
60 hertz.
Right.
So there's 60 cycles, so that one sine waveform, 60 of those per second at 120 volts coming out of your wall socket.
And it's actually very accurate. It doesn't vary, but a fraction of a hertz.
Unless you're Meredith, it's probably 50.
Right.
So
Your-
if
your
you,
view is 50.
If you stick your finger in the socket, there'll be 60 times during that first second that you're not getting shocked.
No. Oh, but you're not? I was gonna say, you're gonna have 120 pulses.
Right. But 60 times that you're crossing 0 and not getting shocked.
Okay.
Is there any correlation between, the frequency and the power that's running through? Like if you have a 220 line in your house, or 240 watt. Would show different waves.
They're all at 100, they're all at the same frequency.
They're all derived from the same generator.
It's just,
Difference in the United States, we use 60 hertz. A lot of countries, mostly in Europe and Japan, we use 50 hertz.
Yeah, why is it? Why did the rest of the world go 50 and the US at 60?
That's just the way.
We
Yeah,
like,
did it
we like
metric?
being different.
well, same reason that most of the other world is not 120 volts also.
They're 100 volts or more.
We measure things with the metric system.
And why does
Yeah,
the military use 28 volts?
I don't know that.
But they do,
A lot of places they use 400 volts.
400 hertz.
On Tesla, we're using 800 volts DC.
Oh, for the batteries?
Yeah.
So the answer is, we don't know.
Okay. There's a lot of things that are just convention and in some way, it started and we just keep doing it.
I'm gonna guess it's how they built their grid.
So we should have stayed, we should have stayed DC rather than going to AC.
Oh, you sound like Edison.
Yeah, I was gonna say, 'cause New York was originally. DC.
Edison lost. It turns out that you can't transmit DC power effectively, which is why Westinghouse won, sort of. Although it turned out to be General Electric, which bought them all up and whatever, but
Long distance distribution.
yeah.
It's easier on AC than on DC when you go hundreds of miles from a generating station.
And especially when you up the voltage, which is hard to do with DC. Where you
And
can,
probably also why we went with a combustion engine rather than electric back in 1900.
yeah. Okay, so pulse rate, sometimes they throw these weird left base things in there like pulse rate, which is heartbeats per second. Speed, which has nothing to do with it. We will talk about velocity of the speed of light, but not necessarily the speed. It usually refers to revolutions per second, or like in your car, how many miles or kilometers per hour you're going. Wavelength, we'll talk about in a little bit, which is how far the wave actually travels in one cycle. Or so it's like the period, which is the number of seconds, wave or a cycle. Well, if it's traveling at the speed of light, then it's the speed of light times that time. Okay, so that would give you how many meters or inches or whatever,
Is that
which we
why-
call the wavelength of that cycle.
Is that why the bands are called 10 meters,
Yes,
6 meters?
Yes.
So on,
yes,
physical length of the wavelength?
right. Absolutely. And that's how antennas, right?
Depending on what frequency you're
For
trying
them to resonate, they need to be at a quarter, half wavelength. So what is the unit of frequency?
Hertz.
Hertz. And it's a proper name, therefore it's a capital H, little z. That's on the test. Henry is a unit of inductance we haven't talked about, and a farad is a unit of capacitance we haven't talked about yet. And a Tesla, not named after the car, but Tesla himself,
Nicholas.
is a measure of magnetic flux.
And in 20 years, it'll be called an Elon.
Okay, so now we have resistance, which is the opposition to the flow of current. It doesn't matter if it's DC or AC. It's not frequency dependent. Resistance is pure resistance, opposition to current flow. Now you'll find that we have things called impedance and reactance, which are frequency dependent, which we'll talk about in a little bit. But resistance is purely resistance to current flow. It doesn't matter whether it's alternating or not. And we measure it in ohms. And we a lot of times use this Greek letter omega because it kind of sounds like ohm to represent it. So what are the units of electrical resistance?
Ohms.
So we haven't talked about admittance, but Siemens is how we measure admittance, which is the reciprocal of impedance, which we also haven't talked about yet. Mohs are units of conductance, which is the reciprocal of resistance. That's why it's ohms spelled backwards, Mohs. Ohms is the unit of resistance, and coulombs are the unit of charge. So if we repeat these enough, you'll remember all of them. So what type of current flow is opposed by resistance?
D.
C.
Good. So direct current is opposed by resistance, alternating current, RF current, any kind of current.
RF current is AC current at a very high frequency.
Well,
Or an I.
VLF is not high frequency,
You're right. It's higher than 60 hertz.
but technically, I guess 60 cycle wall stuff is
Yeah, that's.
RF, except it doesn't radiate very well.
We'll have to debate enough things.
Okay, conductors. Usually these are metal. We tend to use copper the most. Silver is actually the best. Copper is like next. I forgot, is it aluminum or gold next? I think gold and then aluminum.
Not very good.
Huh?
Gold is a very good conductor.
Yeah.
I understand.
Too expensive.
Gold is the best conductor, which is why we use it in semiconductors, right?
No,
Or.
it's not.
It's not, what is the best?
Silver,
Really?
yeah.
So
Of the metals,
all the CPUs and everything is, they use pure gold, 24 karat gold. things
We
like
use
pure
gold
chips and-
Because it doesn't corrode.
because, right. We use
The
it to,
reason they put gold contacts is because with silver contacts, you can get corrosion on it. Or
it
use
oxidizes quickly, and copper oxidizes. Gold doesn't. Gold is,
Is the worst of all for oxidizing.
what it,
Aluminum.
oh, aluminum, yeah, aluminum
What
oxide.
is out there on those wires.
That's why you use a lot of Noah locks when you install it.
Right.
It's aluminum, those wires out there.
Yeah, I think the
Talk
next,
about Superconductors, which.
yeah, right.
Gold. They can go into profit one. That's a serious consideration. If you're building this, as your business. If I put little dab of gold versus a little dab of some other metal,
Yeah.
if I can increase my profit margin over the cost of the gold. And because of the complexity, a lot of people just back off and not question it.
I never thought of that.
It
I
always
went to a
goes-
chip
it
maker and I
always
saw
goes
the bars
down-
of gold.
It always goes down to the money. Always about the money.
Yeah.
And the superconductivity comment got shot down last night. If you hadn't heard, they're talking about selling off our helium reserves.
Okay. Conductors. We normally use the conventional metals, although there are some of the funky elements that might actually be a better conductor, particularly at low
Some of them are
temperatures.
called semiconductors.
No, semiconductors are different. We will get to those later. And we use these to connect components, and have a path for current to flow or charge to flow. And the reason we use metals like silver and copper and aluminum, gold, is they have many what we call free electrons, which means the electrons in the outer shell, usually there's one. It's very easy to displace that electron and have it move around. And in some cases, some of the metals like copper at room temperature already have free electrons without even applying a voltage. And they're just roaming around, going from atom to atom. What these little diagrams are showing is you've got free electrons running around there in a random fashion. The more the temperature of that piece of copper goes up, the more of those free electrons you're going to have, because there's more energy in it, and it takes energy to raise them up to a level to be free of the atom. So you get more activity. If you had that at absolute zero, then you wouldn't have any electrons moving. Except in the special case of superconductors where they get close to zero and they do get conduction. But that's well beyond this. When I apply a potential, some force, okay, then I can attract those charges and cause them to move. Because they're just static charges. And any of these demos that you see, like, charging up a balloon and stuff, that's actually, you're putting charges on the surface of that balloon, and it will attract or be attracted to other charges. That's actually what's happening in here at the atom level.
What kind of current you have flowing in that right graphic? Direct or alternating?
It's
No, it's
okay.
pretty simple.
It was actually in that one, well, they called it electron. It was actually charge flow going in the opposite
Right.
direction.
Direct or alternating. So it's direct current, so the battery and all the power.
Right.
Going in the same direction and never reverse, so.
No, it's not anyway. This is a typical way an atom is represented. In this case, it's copper. I think this is the Bohr, what they call the Bohr model, where you have all these different shells, let's say. And there's some structure as to how many electrons you can have in each one of the shells. In this outer shell, you can have up to 8 in this case. Copper only has 1. So it's very easy to free that 1 electron. And we call that outer shell, regardless of which layer it is. The outer one is always called the valence layer. And that's where it can combine with other atoms to make crystal structures and things like that. This one is showing the difference in energy levels between conductors, semiconductors, and insulators. And if you notice, this vertical axis is the amount of energy. Okay, and you see there's an overlap in the energy in the valence band, which is that outer shell, and what we call the conduction band, where electrons are moving around. So in like case of copper, at room temperature, you've got some electrons that are already over here in the conduction band and moving around. So it's very easy to attract them with a charge or a voltage force. In the case of a semiconductor, you have a big gap, energy level difference between the valence band and the conduction band. So it takes a lot more energy to move an electron from the valence band to the conduction band. And in normal cases, like this with silicon or germanium, it's not going to allow current flow. Okay. At least not very well. We do things like doping it, and we add impurities to the silicon to give it a positive or a negative charge, which is how we make semiconductors, by using impure silicon and making junctions of them, and we'll talk about that a little bit. In the case of an insulator, this energy gap is very, very large. So it takes a tremendous amount of force to get one of these electrons to actually go to a high enough energy to move. And usually on an insulator, you don't see that happen until you have enough voltage there to break down the insulator. It arcs over, or it just starts to heat to the point where it melts or something. Okay. This is the resistivity at essentially room temperature for different materials. You see silver is significantly better than copper, but the little dollar signs show it's much more expensive than copper. At least it used to be. I think copper is catching up. We don't use gold, even though it's not nearly as good, because it's so much more expensive. I mean, gold is over $2,000 an ounce. Silver is 30-something an ounce. I'm not sure what copper is. Aluminum is not too much worse than gold. It's cheap, so it gets used a lot. It does have the problem of oxidizing, same as copper, which is only a problem at connections. In a copper wire, it's usually coated with a jacket, which protects it. And you normally do something at the connection point to offset the oxidation. And the same kind of problem with silver. It's just too expensive to use for normal, everyday kind of wire. They probably used it at Oak Ridge doing the nuclear research stuff because money was no object.
Another big advantage with aluminum, especially when you get up into 500 MCM and the larger sizes, is it's something that you can take and hand turn and bend. And when you get up into copper in that size, it takes hydraulic bender to bend that wire.
Yeah. Okay, so why are metals generally good conductors of electricity? Free electrons. All metals are not necessarily high density. Lithium is one. Sodium is a metal. They're float on top of water. Of course, they catch on fire when they do that.
Yeah.
But there are no such, in normal cases, there's no such thing as free protons. They never leave the atom. Now, maybe in a collider or something, you can do that, but you can have an electron leave the atom, which leaves the atom positively charged because it's got more protons than electrons. But the protons never leave the atom.
Neutrons won't let the protons get out of the.
I don't know what the
nucleus.
neutrons do. They just add weight. Okay, so insulators are non-metals. They do not conduct. A lot of times we call these dielectric, like in the case of capacitors or in coaxial cable, feed lines. It's the insulator separating the conductors. Plastic, glass, ceramics are what's normally used. The same resistivity, if you compared the numbers, you can see how much bigger these numbers are than the metals. And you notice that silicon is fairly high. It can act as an insulator under normal conditions. And it's actually why we use it as a substrate in an integrated circuit, because it's an insulator and then you dope certain areas to make them semiconductors. This is just another one talking about conductors can have 1 to 3 valence electrons. The best ones have one, like copper and silver. Insulators are usually close to being, the shell is full, so they'll have 7 or 8 valence electrons, which is one of the things that, and I don't understand the physics, that makes it very hard to displace one of those electrons. So which of the following is a good electrical insulator?
Glass.
All right, we measure current in amperes. It's equivalent to 1 coulomb per second. These are hopefully what you've learned. Direct current flows in one direction. Alternating current changes direction per cycle. Electromotive force measured in volts is the force that causes current to flow. Frequency we measure in hertz, the number of cycles per second, or hertzes. I still like cycles per second. Resistance in ohms is the opposition to any kind of current flow. Conductors are metals that have many free electrons, and insulators are nonmetals having tightly bound electrons. Any questions on those?